Hello everyone, welcome back to a new episode of Advent of Code. Getting a late start again today. We're going to move on to day 8. Day 8. Space Image Format. The elves' spirits are lifted when they realize you have an opportunity to reboot one of their Mars rovers, and so they are curious if you would spend a brief sojourn on Mars. A sojourn is a journey, right? Spending a brief sojourn is weird. You would He's not sorry. Well, fair enough. I guess, okay, so Sojourn is a Mars rover, right? I assume. I would have written take a brief sojourn to Mars. I don't know that you spend a sojourn. Maybe I should look that up. But anyway, you land your ship near the rover. When you reach the rover, you discover that it's already in the process of rebooting. It's just waiting for someone to enter a BIOS password. The elf responsible for the rover takes a picture of the password, your puzzle input, and sends it to you via the digital sending network. Ah, Deep Space Network. That's what this joke is about? Anyway. That's a thing, right? The Deep Space Network is like the communication medium they use to get Mars pictures? I don't know. Anyway. Unfortunately, images sent via the digital sending network aren't encoded with any normal encoding. Instead, they're encoded in a special space image format. None of the elves seem to remember why this is the case. They send you the instructions to decode it. That's software for you. Images are sent as a series of digits that each represent the color of a single pixel. The digits fill each row of the image, left to right, then move downward to the next row, filling rows top to bottom until every pixel of the image is filled. Each image actually consists of a series of identically sized layers that are filled in this way. Wait, I thought we have rows and columns and also layers? Okay, got it. Yeah, so it's like a three-dimensional image. Okay. So the first digit corresponds to the top left pixel of the first layer. The second digit is the pixel to the right of that on the same layer. And the last digit is the bottom right pixel of the last layer. Okay. So yeah, here's like layer 1, layer 2. So it is a three-dimensional image. Okay. 3 pixels wide and 2 pixels tall. The image data, blah, 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 corresponds to, yeah, fine. So our image is 25 wide and 6 tall. To make sure the image wasn't corrupted during transmission, the elves would like you to find the layer that contains the fewest 0 digits. The layer. So, like the most faithful representation of this would be as like a three-dimensional array, which like Haskell has good support for arrays. I would have to look up how to do them properly, but you know, it exists. But for part 1 at least, we need almost nothing about like this representation. It's just like the width is 25, the height is 6, so we can split the image that we're getting up into groups of 150, and that represents the whole layer, right? We'll have to do something fancier for part 2, but part 1 is very, very simple. So let's do that now. First, let's grab our input. And update the Cabal file, which means I'm going to have to restart the Emacs. Actually, I don't have a thing open yet, so this is fine. Although I do have to, like... Oh, also it's day 8 now. Not 7. So I have to stack build here first to get the split package. I'm planning to use chunks of, which is in split, so that was sort of what the point of that was. Import data list split chunks of. So our input here really, like, I don't know, it's just a string. Like, there's very little to share between, because I assume in part 2, the fact that, like, layers have rows and columns will matter, but so far it doesn't. So the width is 25, height is 6. And pair is just identity, I guess. Well, not quite. You know what? Actually, it makes sense for our input to be a list of string after all. Because then we can be... No. Yeah, okay. Because in part 2, we'll have to split it apart, but we don't need to do that for part 1. We'll just split it into chunks of 150, right? Excuse me, I want to change to part 1, not part 2. Get an int. Part 1 is, so what is it we're computing? The layer with the fewest zeros, multiply the number of digits by the number of ones by the number of twos. Let layers equal, this is like a simple way to do it. I'm sure there's a way to do it with function composition, but I didn't really want to because of having to compute 2 different results on each layer. Anyway, so layers equals, hang on. So actually, what does the input look like? Is it, yeah, it's just a single long string with no, I guess I should open Emacs to double check, right? Yeah, it's all one long line. Great. Chunks of width times height s best layer equal maximum by. So the best layer is maximum by length filter equals 0. And actually I want minimum by, right? Yeah, minimum. Okay. Layers. Score. Oh, I actually, right. Oh, whatever. Let's find a little function called count. Count of n equals count n layer. Score is count 1 best layer times count 2 best layer. There are ways you could write this with less duplication, but I guess I could have just returned this, huh? Oh, filter n, not filter equal n, not count. We actually don't have ints, right? We have characters because we didn't bother to do any parsing at all. Comparing. Yeah, minimum by takes a function to compare 2 items, not a function to compute an int for a single item. So I always forget that because I'm used to closures minimum by, which does the opposite. Okay, well this looks plausible. Like, what does main tell me? 0. All right, nailed it. That's probably because the last layer is a single new line. Yeah, that makes sense. There you go. 2375. That's the right answer. Okay, so let's commit this. Day 8, part 1. So we did basically no prep work. We have no help for part 2. Right? Okay, now you're ready to decode the image. The image is rendered by stacking the layers and aligning the pixels with the same position in each layer. Sure. The digits indicate the color of the corresponding pixel. The color of the corresponding pixel. What? Okay, I guess we'll... Okay. Let's read on and maybe this will make sense later. The layers are rendered with the first layer in front and the last layer in back. So if a given position has a transparent pixel in the first and second layers, a black pixel in the third layer, and a white pixel in the fourth layer, the final image would have a black pixel because we ignore the transparent pixel in 1 and 2, but the black pixel is the first non-transparent one we see. Okay. So this all makes sense. 0 is black. Yeah, so 2 is transparent. So they're highlighting here the colors. What are they highlighting? Oh yeah, they are. Okay, so this one is highlighted because it's all the things it's behind are transparent, so you can see it. Likewise, this one is behind transparent things, and this 0 is behind transparent things. So these are the actual pixels being rendered. Full image can be, What message is produced after decoding your image? I see. So we need like a way to render this a bit. Okay. So I was imagining a 3D array, but I wonder now whether like a list of arrays would make more sense. Or like, I can process this whole thing lazily, right? Scan over all the layers at once. Like, yeah, in fact, we don't even have to turn it... We don't even care about the rows and columns until it's time to render. We can just split it into these chunks of 150 and then do all the transparency detection, and then when it's time to render, break it into rows and columns again. At last, I should say. So that's like kind of shocking to me. I thought I would need arrays, but I don't think I'm going to. Yeah, and then once we get to render the final result, we'll just take the final single layer we've computed, get it in chunks of width, and then like interpose a new line and print it, and it'll be perfect. So, okay. Let's move this here, since it actually, it turns out, is being shared by all of them. still get the same answer? Yeah. All right. Layers. So we need a function which zips together an unknown number of things, applying a function to them, right? And that's what zip lists are about, right? I mean, I could just compute the list and but like I want my function to be general. Like if I got a larger image, it should still work. And I believe a zip list would do that. Let me just go like look up what exactly is the API for zip lists again. Like they're in control applicative apparently. And I think I understand it. It's just like, so it takes, tell me about zip list. An applicative functor based on zipping. So we're basically going to produce a bunch of zip lists, one for each layer. I don't think this is what I need. Because this would make sense if I had a function that knew how many... If I knew how many layers I had, I could apply an n-ary function over each layer, zipping them together with zip list. But that's not quite what I have, right? I have like a list of strings, right? And do I just want to transpose? I guess that's, I think I might just want transpose. Let's play around in the REPL a bit. So suppose that I had the input like ABC, 1, 2, 3, right? And I want to see the first, I want like, yeah, I think I just want transpose. Where the heck is Haskell transpose? Not that weirdo, like data list? Okay. Yeah, so we get back a list that is the same length as each of the input lists, whose first item is all the elements from all the first elements from each of the lists. Yeah, so all I want to do is transpose here. Let pixels equal transpose layers. Oh, finally, the fact that I'm returning a tuple is actually going to make it render a bit weird, isn't it? Oh well, we'll work that out when we get there. So pixels. So now we just want to say image equals map head dot drop while equal to 2 over the pixels in interpose. That's a function, right? Haskell. It's like intercalate, but it's not. I know in Clojure it's called interpose. Intersperse is what they call it in Haskell. Okay, I mean, it type checks. Main? Oh, right. I don't want to intersperse it yet. I need to... we take an image. Okay, right. Chunks of width has given us now a list of strings. So what's intercalate do? Concat of intersperse. Inserts the list. Okay, so I actually do want intercalate. No, I want unlines. Silly me. I forgot that exists. So this is going to look ugly, right? Yeah. But it looks about right. We just have to actually edit main for a change. Print part 1 of input. And then put stir part 2 of input. Right, print is going to take us an int and show it. Put stir is just going to print the string as is. There we go. So this definitely looks sort of like it's supposed to be an image. RKHRY, I guess. Well, let's give it a try. Or hurry was the image for us to get. Okay. Yeah, a nice simple one this time. Nice not to have more int code, to be honest. Oh. Day 8, part 2, and we'll just go edit that, say 8. Anything remarkable here? Not really. I mean, I guess we could get rid of control arrow, maybe? I guess, like, we already talked about the insights for part 1, which were that, like, since you only care about things at a layer-wide level, you don't have to bother splitting it into rows and columns at all. And so then it's just like this minimum by, which is like the kind of thing Haskell's great at, right? Like filtering lists, computing properties like of items of lists. Haskell's great at that. And then part 2, just finding the right function to do the like to get all of the relevant pixels for a coordinate together at once. It seemed like zipping, but I guess the point of zipping is that you should know, even if you're using like a zip list, at some point you have to know how many things you're zipping together. It's not that interesting to zip together a list of arbitrary size. And transpose is great because it takes a list of lists and kind of, I mean, transposes it, right? But like, it still is not like totally easy for me to visualize why it is that transpose does the thing we want, but it does. We have a list of pixels, or a list of lists of pixels, and instead we kind of want a list of pixels of lists in a way, right? And that's what transpose does, is it like flips that last the second layer so that you get a list where each item is like the pixels that would go in, all the pixels that contribute to this point. And then you can just like run a function over them that computes what would be showing, and that's pretty simple. Cool. Okay, well, nice to have a short one, I guess. Thanks for watching, and I'll see you next time.